Hello, my name is Sergey Leksikov, and I work at LabRap as a researcher. And before that, I was working as a data scientist at Foodgood on various data-driven projects. Also, I graduated KAIS, and I participated in PyCon in 2020, where I presented the topic of using AI for infection risk prediction. The purpose of this presentation is to introduce some innovative large language models and Python-based open source projects that help automate complex CLI tasks. I will also show how to use those tools to make an automation project. This is our agenda, from introduction of problem statement to a solution and showcasing a demo. Let's talk about some common challenges with CLI environments. First is about their complexity. For example, GitHub CLI command has more than 100 commands with numerous options, arguments, and nested structure. This makes very hard for new users to learn and remember all the commands. Another reason is that CLI environments are error-prone because of manually typing commands often lead to mistakes and typos, and resolving those issues takes some time. Now let's look at why integrating language models with CLI is important. First, there is a natural synergy between them because they are both text-based. Language models excel at understanding text, which makes streamlining interaction easier. With automation, user can give simple text commands and get the system to do complex tasks. On the backend side, language models can help generating precise commands with automated putting, setting parameters and handling errors. Imagine a scenario where a data scientist needs to train a machine learning model across multiple cloud instances to deploy it and monitor its performance. Normally, this would involve setting up a container, managing resources, and training various commands manually. But with Hertzman, the data scientist can do it all with a single text prompt. For example, with just one text prompt, Hertzman can receive command from user. It can set up cloud-based environment with required GPU resources, automatically pull the dataset and model from repository like Hugging Face, fine-tune the model in distributed fashion, and deploy the model for the real-time inference. Our tech stack includes backend AI, TorchTune, and LangGraph. LangGraph is an open-source Python library inspired by Pregel, designed for building stateful multi-actor applications with large language models. It's great for creating agent and multi-agent workflows, offering key benefits like cycles, controllability, and persistence. It also integrates well with LangChain, another open-source library. Backend AI is an open source, Python-based platform using Docker containers for machine learning application development and management. Backend AI provides resource allocation and isolation, allowing users to create computing sessions for code execution and container management. Finally, TorchTune simplifies the fine-tuning of models, making it easy to optimize machine learning models with just a few commands. LangGraph is designed to create agents with graph-based approach. It supports features such as cycles and branching, allowing you to implement loops and conditionals in your applications. One of its key benefits is persistence. It automatically saves the state after each execution step, so we can pause and resume execution anytime. This is useful for error recovery, adding human-in-the-loop workflows, and even time travel, reversing operations. Human-in-the-loop support lets you interrupt execution to approve or edit the next action planned by the agent. It also supports streaming, meaning you can stream outputs from each node as they are generated. LangGraph core components include nodes which define the computation logic, edges that define the direction of the flow, and shared state across the system. Backend AI is a versatile platform that supports a wide range of users, from data scientists to students. It provides easy access to GPU resources through tools like command line interface, web GUI, SDK, and web servers, making distributed computing and application management simpler. The Backend AI Manager handles tasks like managing multi-container sessions or GPU applications, and Backend AI Agent, it does monitoring performance, security, and GPU virtualization. The Backend AI CLI is a powerful tool, much like a Swiss knife for developers. With just a few commands, users can create sessions with allocated resources, select the appropriate Docker image, and even attach a cloud storage. This makes managing complex machine learning workflows more efficient, all through a streamlined, user-friendly CLI interface. TorchTune is a PyTorch library designed for easy authoring, fine-tuning, and experimenting with language models. It focuses on 4 key aspects: simplicity and extensibility. It's built with native PyTorch and has a componentized design that makes it easy to reuse and extend its components. Correctness. The library emphasizes proving the correctness of its components and recipes. Stability. Like PyTorch, TorchTune is designed with smoothly and reliability. Democratizing language model fine-tuning. It works out of the box on different hardware, making language model fine-tuning accessible to everyone. With just a few simple tune CLI commands, TorchTune allows users to easily download a model from Hugging Face, fetch dataset, select receipt, and begin fine-tuning. When integrated with Hetzman CLI agent operator, this process becomes even more streamlined, making integrating language agents more efficient and reliable. Let's have a look on system architecture. Our system architecture revolves around automating command lines execution using AI agents. It works in 2 stages. In stage 1, we build a vector store. The crawler language model scans and extracts descriptions, arguments, and options from Backend AI and TorchTune CLI commands, organizing them into a structured YAML format. This data is vectorized and stored in a format database vector store, allowing for fast retrieval during command execution. Admins can also enhance this database vector store by manually adding some useful use cases and summaries. In stage 2, the system handles user interaction and command execution. The supervisor agent, the Hetzman CLI operator, interacts with user, verifying or refining commands like upload my Python code to a specific session. The Backend AI executor agent retrieves relevant documentation from the vector store. It generates the shell commands with the right arguments and executes them in an isolated session managed by Backend AI. A feedback loop ensures that results are propagated and returned to the user. Using LangGraph allows for efficient cycling and iteration between components, ensuring the system is flexible, accurate, and powerful. LangGraph enables here building agentic workflows using graph structures. The core idea is that there is a shared graph state, defined as type dictionary. It's accessible by all nodes in the system. Nodes in LangGraph are functions that handle various tasks like input and output and processing. Each node receives input from the shared state, processes it, and updates the shared state with the result. Edges define the flow between nodes. Direct edges control the basic flow, while conditional edges have handlers deciding which node to go next. Handlers in LangGraph manage transactions using logic based on simple if-else conditions, or even decisions made by language models based on their output. In this LangGraph architecture, the assistant acts as central coordinator, managing various tasks and calling the appropriate tools. The assistant can access search functions through assistant tools, allowing it to look up necessary information or documentation. The backend AI executor has direct control over the backend AI, handling commands and managing sessions. It uses backend-specific tools to execute tasks like resource allocation or container management. Similar to Torch-Tune executor, manage tasks related to model fine-tuning using Torch-Tune tools. A key strength of this architecture is robustness enabled by existing of cycles. When an error occurs during low-level code execution, each executor node tries to handle the issue first. This could include fixing common mistakes like incorrect options or arguments. If the executor is unable to resolve the error, the problem is escalated above to the assistant, and the assistant tries to search for more additional information in the documentation or knowledge base to assist the executor in resolving the issue. The feedback loop ensures that even when an error occurs, the system can correct itself and continue operating smoothly. So benefits of such a system is that it's fault tolerant, it has feedback loops, it's very modular, and at any stage you can integrate a human in the loop, and also it's transparent and explainable. This project is vendor agnostic. Instead of backend AI, you may use Docker, Swarm, or Kubernetes. And instead of Torch-Tune, you may use Hugging Face to build your own system. So there is a demo. You may see the link at the end of the presentation. And I will go over screenshot use cases. So the demo was made using Radio UI, Python-based library. The main interface is a chat interface. User inputs text into a message box below. For example, user asks what the agent can do, and agent replies the summary of everything what it can do to the user in the box above. Then at the box below, user asks to create a new session, and agent will create a new session, and user can see the information of detailed information of this session. We can verify that session was created on the backend AI cloud web GUI. Here we can see that a section was created and it's active with those allocated resources. Going back to our agent app, let's ask agent to list sessions, and we can see that this session was listed with this specific session ID. We can ask agent to provide more detailed information. Now we can see CPU and memory utilization of that session. We also can ask and see the result of which language models are available for training with TorchTune library. So TorchTune provides the list of those available sessions. Let's ask our agent, Felixman, to install TorchTune in a remote session, which we created before, and start fine-tuning Llamas 3 model. So fine-tuning started, and the language model agent, if some parameters are not specified, the language model tries to decide about those parameters. And here we can see that session is started and GPU utilization is 100%. We also can request to list some information from the log file about recent training loss output. And here we can see that loss is 2.45, which is basically at the beginning of the training. Let's go deeper and discuss some implementation details. So here we have three important files: main.py, model setup.py, and agents.py. In main.py, we define the graph and load agent objects. At model setup, we load configs and text prompt templates. At agents.py, we define chain sequence of text template, chat API, and agent tools. Then we define nodes based on agents. Here's template used by the AI assistant for operating backend AI and TorchTune CLI operations. This template allows the assistant to search for commands, provide relevant information, and interact with backend AI and TorchTune executors. This template is loaded into the context memory of language model. These executors handle commands and operations in remote sessions using like backend AI SSH or Fabric. The assistant uses this structure to understand which command options and arguments are available and find relevant documentation and provide examples. If you look closely, this template has some placeholders for loading external key information like summaries, comment example, default settings, and some system configuration settings. In this implementation, here is search tools available. Search tools are defined for the assistant language-based agent using the tool decorator. This decorator allows us to specify a tool for language model function call. When the LLM calls a tool, it fills a predefined schema with values such as the tool name and its arguments. In this example, the search docs function is used to query documentation for backend AI CLI operations. It provides the system with context, reasoning, and step-by-step logic to find correct commands and options. It uses a vector store to retrieve relevant information based on similarity search, ensuring the results and that are accurate and relevant and helpful. This code defines the load assistant template function, which loads a text template from a file and populates it with relevant data for the assistant. The function reads the template file, formats it with necessary configurations, such as access key, group names, and default Docker images, and then returns the formatted template. This is essential for creating dynamic chains where the assistant uses the provided configuration to interact with backend AI, generating commands and executing tasks. By structuring the template with these variables, the system can handle multiple scenarios and configurations efficiently. This part of the code shows how we create an assistant chain. After the template prompt is loaded, filled with variables, and those are defined, we wrap everything into an assistant chain abstraction. In this create assistant chain function, we use the chat prompt template to define the primary assistant prompt. The system message is built using the field template, and it can handle multiple messages through placeholders. This chain structure allows the assistant to execute tasks step by step, utilizing all the configured tools and components in one cohesive flow. In this part of the code, we are creating chains which are the core components in the LangChain library. Chains are essentially a sequence of steps that are executed in specific order. For example, in this case, we create assistant chain using a text prompt template. Variables are filled into template, and then the chain makes an LLM API call to process the input. Similarly, we have executor chains for backend AI and TorchTune. These chains also follow a similar pattern but are specialized to handle their respective tasks like resource allocation with backend AI or model fine-tuning with TorchTune. In this part of code, we are loading various configurations and templates necessary for the language model-based agent. First, we load the configuration files, which help define important setup details for the agent, such as the model name, memory usage, and document summaries. These configurations provide the foundation for the language model-based behavior. Next, we load text prompt template for the language model. These templates help format the commands and requests the language model will process. Once the configurations and templates are loaded, we create chains for assistant, backend AI, and TorchTune operations, allowing the system to manage tasks in structured and efficient manner. In this code, we define the core structure of the graph. First, we define the state of the graph using state graph, which is a typed dictionary, and it will maintain the shared data throughout the workflow. Next, we define the nodes, starting with assistant node. This node uses the assistant chain with specific configurations like callbacks and maximum iterations. Then we define the assistant tools node, which includes error handling using a fallback mechanism. Finally, we define the edges, which dictate how the nodes are connected. Conditional edges are set between the assistant node and tool executor, backend AI, and TorchTune, ensuring the flow transitions correctly based on the tasks being executed. The end node signifies the completion of the process. In this section of the code, we are compiling the graph and setting up an input and output interface. First, we compile the graph using graph builder compile function, storing it in memory using the memory saver. After that, we define a looping mechanism where the system continuously receives the user input. If the input is valid, it processes the input using the graph, streams the output, and displays the response to the user. The loop can be executed by user typing Q, which triggers the system to stop receiving inputs and gracefully exit the session. In this system, a node is essentially a function that processes input from the shared state and updates the state with the result. The input to a node can be the last message in the conversation or group messages. You can define the logic inside of the node and control the flow using if-else statements or making LLM API request calls. I just defined the flow between nodes, determining the direction from one node to another. In this code, the assistant node is defined. Init method initializes the assistant class, sets up the assistant chain, and the call method allows the class to be invoked as a function. And in the call method, the actual processing work happens based on the state of the graph. In this section, assistant node. In the assistant node, we start converting and extending the message history using the convert to message functions, ensuring the format is suitable for processing. The assistant invokes LLM chain with a runnable method. Next, the edge handler function, they do routing here based on if-else condition based on the most recent message in the graph state. Today we have seen how language model can revolutionize command line usage for non-technical users by simplifying and automating complex tasks. We walk through the architecture and flow, showcasing how even the most complex CLI clients can be transformed into intelligent AI agents with the usage of LangGraph, backend AI, and TorchTune tech stack. With the power of the LangGraph library, we demonstrated how easily multi-agent systems can be built, amplifying interactivity and adaptability. And this isn't just about enhancing systems, it's about delivering a whole new level of user experience and boosting operation efficiency like never before. So future development can be done like providing multi-GPU training and multi-session management, and we can enhance this AI agent by making it learn from previous user interaction and previous interaction with the system and environment, and also adding task execution in the background so an agent can check the progress of the task later. So this is open source projects which were used, GitHub links for them. Thank you.